Morning. Today is January 10th, and this is our sixth week after first exam. So this is the week before the last one. So we have to be worried about closing this. Okay, now today, Engineer Isaac. Well, I'm going to review just a little bit what you were supposed to read yesterday. Not only read, but do practice with ANSYS. Then Engineer Isaac will going to review in detail all of this, and we're going to complete an exercise. Hopefully, we will be able to do that in the first two parts of the session. And then in the last part of the session, I would like to do a progress control of the project. So by now, you were supposed to, we are expecting that you show us in detail all the structure, okay? And also, we want you to explain us about the loading conditions that you're going to apply. You see, I don't want you to tell me, yes, I'm going to apply to loading conditions. No, we want you to tell me or to tell us, Genesis and Engineer Isaac and myself, details of that. Okay, so for example, you said, I'm going to consider the corrosion. Okay, how are you going to consider that? How much is the percentage? Because that, otherwise, that means that you have not prepared that. If you have not prepared that, you just tell us, okay? But the thing is that you see that with our question, we are telling you if you are up to the level or you are behind. If you are behind, you still have time to complete it, but you have to put extra effort. Okay, so that's the agenda for today. Genesis, can you see my PowerPoint presentation?
Yes, doctor.
Okay, this is what I sent you yesterday. And you see here that this is number 2. So this is the second activity in this chapter, okay? You were supposed to complete this. It's just a quick practice, and that's all. If you did it, if you try to do it, it's going to be easier for you. If you didn't, well, it's going to be a little bit harder. But in any case, Engineer Isaac will review all of these steps to complete this exercise. Last session, we analyzed a structure composed by beams, frame, and shafts. So there were line elements, okay? In this case, we are considering a model which includes plate elements, okay? Every plate element is something that we explain, but in any case, maybe I can insist on this. Let me take this tablet. Okay. See, if we have a plate, okay? This is a plate element, okay? In general, we can have this type of discretizations, okay? So in this case, each one of these 4 joints will allow us to do an interpolation in this element. Okay, now, what's the big thing here that we should have in mind is that this element can sustain this load and this load. Okay, this thing here is, as you can see, this is normal to the surface of the element, will produce bending. And this load here will produce in-plane effects. Okay, this is what we studied in chapter 3. This is chapter 3. Okay, the bending of the plate, we did not analyze here in this course, but you remember the concepts of bending of plates from previous semester. Okay, so in this case, we're going to use this type of elements in order to discretize the structure. And you can see, of course, immediately that the number of joints is going to be much larger. And of course, that means that the type of the number of calculations that the computer has to develop is higher, of course. Okay. Let's see. So, so this is the structure that we wanted to analyze. This is the exercise. So it has a plate. At least it has 2 frames, side frame, bottom frame. It corresponds probably to a fishing vessel because you see that we have a dead right angle. And here you have the dimensions of the frame. Okay. Since this is the geometric, I'm sorry, the structural element. And here you see that you have to include the dimensions. And this is something which is very, very recommended. Okay, you immediately see here that we have taken the time in order to include the name of each element. Okay, so since you will see in that in your structures, you have a lot of elements. In this case, you immediately can identify who is who. So this is something which is extremely recommended, highly recommended. Were you able to assign a thickness to each one of the elements, Mr. Leon? Mr. Leon, did you complete this exercise? Mr. Leon, did you complete?
Good morning, doctor. Yes, I tried to do it.
Did you assign the thickness to each element?
Yes.
Okay, good. It was just, and then using this path, you could generate a mesh. Okay, remember, mesh is the same as partition of the domain. Okay, in this case, we have to be careful because, as we mentioned, of course, the number of joints right now is going to be very large. So if you select a very small size of the mesh, then the number of joints is going to be extremely high. And it will take forever until you get results. So you have to be practical. At the beginning, you can accept to use a large size of element. And then when you try to convince yourself that you are close to convergence, then you should try to go to smaller elements, okay? This is something which is very important, and probably Engineer Isaac will insist, is that you have many elements, right? And the thing is that they have to be connected, okay? So just as a general comment here, people. Okay, for example, let's suppose that you have something like this, okay? Okay, you have something like this. This is a plate. And here, let's suppose that we have a stiffener. So this joint here should be connected to this one here, okay? Please In some cases, it's easy, but you have to be certain that everything is well connected. For example, if you have that the partition of the stiffeners is something like this, you see immediately that the two are not well connected. This joint, okay, which is part of this element, the vertical element, is not connecting to this element here, because this element here is formed by this, and that. So this element here is formed by, let me use different colors. This, and that. Okay, so the displacement of this element here, okay, has nothing to do with the displacement of this edge. And that's something that we mentioned in the previous project. And I asked some of the groups to redo this because the connection was not there. In this case, you have to be certain that you connect all elements in your structure. Okay, otherwise, this area here will have, you will see, it may have very low stress, meaning that you have, it's like having two structures which are not connected. Okay? Engineer Isaac probably, oh, shoot, will insist on that. Okay, here we have a question. Do you remember how to impose boundary conditions? Mr. Diaz, Josué Diaz, do you remember how to impose supports on the boundaries? Mr. Diaz?
Yes, doctor.
How do you do it?
I don't know how to explain you the steps for obtaining it.
But you know how to do it. Well, you better do it. Okay, you better be ready because it's coming. Miss Freire, are you there? Can you explain us how to impose supports on the boundaries? Miss Freire?
Good morning.
Oh. You see that I really like to, when I don't get any answer from somebody, that means that that person is not here. Please, Isaac, can you hear me, Isaac?
Yes, doctor.
Okay, when I ask a question to somebody and that person does not answer, please remove them from this session, okay? And this person will have to, if he wants to come back, he will have to ask permission again. But I want to be sure that I don't waste time, okay?
Okay.
Thank you very much. Okay, so remember that if you do not include enough support conditions, there will be no solution, because the unique solution, because the stiffness matrix is singular, so it has no inverse. So you have to impose boundary conditions. So you have to avoid that it can move as a rigid body. Hydrostatic pressure, this is very, very common for us because we are all the time having this action, this load acting on our structure, okay? And in this case, what you have to do is basically you have to define in the Z direction, see, the level of the water, basically. So in this case, you see that here and up, you have 0, that's blue. And from that point and downwards, you see that the pressure is increasing. So So it's a good idea for you to check this. Mr. Zambrano? Mr. Zambrano?
Yes, good morning, doctor.
Morning. What was the draft? Did you complete this exercise?
Yes, I think I
Draft?
just missed the direction of the pressure because I put like perpendicular to the surface.
Okay. So we have to be careful, because if you want to use hydrostatic pressure, okay, you have to define Z in the vertical direction.
Yeah, okay.
Okay. Can you determine if fails or not? Did anybody get the results? Did anybody was able to get any value of the stress? Mr. Cano, did you get any value of the stress? Mr. Cano?
Hi, doctor.
Oh,
Yes.
did you get any stress? Any stress? Did you get a stress value for this exercise, the maximum? No?
No.
Okay, no problem, no problem. Today we're going to do it. Mr. Galarza, did you get any stress from here?
Good morning, doctor. Yes. I get the maximum value 2.79 Newton over meter squared. And I think that is too low because I use it for the plate 15 millimeters and for the reinforcements 12.
15,
So
that's a lot.
yeah. So
Yeah,
for that
that's
reason, I think that the values are too small.
I know. This is something that we missed since we are in this pandemic. But when you make a visit, okay, and see every area of naval engineering give you some details. If you paid a visit to a ship, right, and this visit is related to ship structure, okay, it's a good idea. For example, if you ask the thickness of the bottom, the thickness of the deck, and you have tried to keep that in your memory.
All
Okay,
right.
for example, you have a 100-meter long ship, and more or less, the thickness of the deck I would expect to be in the order of 10 millimeters, more or less.
Okay. So
So
the thickness
from
that I
that
use
point,
is higher.
exactly. You
All
can, if for example, in a few years, you will have an assistant, and he will do most of the calculations, and you have to review them. And if he comes with a thickness which is very large, the experience will tell you if that number makes some sense or not. You can review the details, but at least in the quick check, you can see that numbers makes or makes not sense. Okay, now let's go to Isaac. Go on in detail what we have reviewed. Isaac, go on.
Okay. Okay, good morning, students. We're going to continue with this exercise, but in this case, we're going to use shell element or surface element. The example, you are asked to calculate the maximum stresses and deflection of performance side plus bottom panel of a ship subject to hydrostatic pressure. This is the geometry. The plate of the side plus bottom panel is 8 millimeters. There are two frames. The profile of the frame is T, and the dimension is 200 millimeters per 16 millimeters, and the thickness for the web and flange is 6 millimeters. The spacing, the frame spacing is 1 meters, around 1 meters, and the other dimension about half of the beam and the deck. Okay. The total length of this block is 3.24 meters. So maybe in these two edges there are transversal ball heads, and in the middle and in the middle of this block there is a longitudinal ball head, and then this is a connection between a strain deck. So the first step, everyone have to draw this geometry using rhinoceros and then export it with EHS format. You can create a new model structural and then import the geometry. So you see that in the previous slide is the geometry is drawn using rhinoceros, and then in this part is in the ANSYS programs. So you can assign the thickness, but it's a good idea that you can define every surface with a specific name. For example, flange 1, web 1, flange 2, web 2, and the plate with a specific characteristic. So you have to select one element, and then assign the thickness. For example, the plate of the panel, the side plus bottom panel. When you complete this design modeler, you have to close this module and then enter to the model. So in this model, you have to specify and generate the mesh and then apply boundary condition and loads, and then select the parameter of the result that you want to see. So you see in this part immediately that the geometry is done, okay? And then you can assign the material that you want to do. So in this case, we are going to use structural steel, but if the material is aluminum, you can create a new material, okay? For the mesh, for this example, we're going to use 2 element size for each element. For example, one element size about equal to 60 millimeter for the plate, because this a big element, and then on second element size equal to 20 millimeter for beams, that is considered to flange plus web. Okay, this is using inserting sizing. Okay, and then when you insert sizing, you have to assign the face and put the value of the element size. The same process in order to insert another sizing, but in this case for all the beams, that in this case the element size is 20 millimeters. So in order to select several surfaces, you have to hold the Control K. So you can see immediately the mesh when you click on generate. So you see the mesh of the beam and the mesh of the plate. But in this picture, you see that there is not a connection between the web of the frames and the plate. So in order to do that, you can insert mesh connection group. This option is to do the connection between the mesh of the frame and the mesh of the plate. Is so you have to click on the mesh connection group and then first detect connections and then generate. So you see the result of the mesh. That's in this case, the mesh of the plate is connected to the frame. So it's better to do that because the frame and the plate is work together. So you have to always check connections between when you have several elements in your structure. Okay, so if you have checked the mesh that you create, you can go to a statistic and then you can see the number of the nodes, the number of the element, and the mesh metric you can select. There are many options to see the quality of the mesh, but in this case we're going to use element quality. Element quality consists is a measure that how distortional is the element related to a perfect cube. So the value of the average must be equal to close to the one in order to the mesh is correct. Okay, try to this value will be close to the one. Okay, so the next step is to put the boundary conditions. In this case, we assume that the border is fixed support in all the edges. So you see in the picture that the all edges is clamped. In the edge or longitudinal, in the middle of the block, and the edges of the deck. So then you can insert the pressure. In this case, is hydrostatic pressure. You can set up. Okay, you have to select the geometry. Okay, you can select the geometry and then specify the density of this fluid, and then the acceleration component, the C direction, and then specify the draft. In this case, the draft is 3 meters. You see that the maximum pressure is in the bottom, and then change from the bottom to the deck. So this is the final setting that you have to have. So this is the geometry. Okay, we assign the thickness, then the mesh. There are 2 mesh, one mesh for the plate and other mesh for the beams. Then check connection between mesh, between elements, okay, and then static structural, you see the boundary conditions and the load. and solutions, you have to insert the parameter of solution that you want to see. In this case, it's equivalent von Mises stress and then total deformation. So you see the results. This is equivalent stresses. So the unit is megapascal, and then the value of the equivalent von Mises is lower to the yield point of the material of the steel. You see total deformations, and the maximum total deformation is between the frames in the panels. So the total deformation is around 3.5 millimeters. Okay. So maybe a student, there are questions so far. There are questions so far? Because after the break, we're going to do in the program. So
well,
okay.
Isaac, this exercise we completed in the previous chapter, right?
No,
Is this no? Okay,
no.
so people, what I suggest is now we're going to the break. Okay, so I suggest that you still, during the break, you start open the Rhino program and start preparing the geometry of this model. Okay, go on, Isaac.
I posted the aula virtual and this material, and then a file with an easy format, the line of the frame. So you can use this line in order to complete the geometry in Rhino.
Okay, let me say something, Isaac, here. People, in this case, for this exercise, Engineer Isaac provided you with the ANSYS file. Remember that you are responsible for being able to use Rhino to prepare that file. So before the evaluation, which is next week, please make sure that you are able to complete it. Okay? Remember, I insisted when we started the last part of this course, that we have the responsibility that allow you to approve this class if you prove us that you are able to work with both Rhino plus ANSYS to analyze an structure. Okay, so let's go now to the break, and in the meantime, please download the ANSYS file that the Engineer Isaac posted in the Aula Virtual. Okay, so let's have a 5-minute break here. Okay.